Good morning, everyone. I suspect that it's appropriate that I am filming or doing this little vignette in the morning because we're going to use my favorite molecule, caffeine, to do some practice problems regarding the concepts of the mole that we've talked about in the previous videos. So in this little vignette, we're going to go over how to do problems 1 through 4 with my favorite molecule, caffeine. But before we do any calculations, let's talk a little bit about the two formulas for caffeine that are down here. This first picture is the structural formula for caffeine. If you remember, structural formulas tell us how atoms are connected to each other through bonds. Underneath the structural formula of caffeine, right here you see the molecular formula for caffeine, C8H10N4O2. And if you remember, molecular formulas speak to how many types of atoms there are in the actual molecule. Now, molecular formulas are different than empirical formulas. You remember from previous video, empirical formulas are simplest whole number ratio of atoms in a molecule. And I mention that here because in subsequent videos in this chapter, we're going to talk about how to calculate empirical formulas. Right now, you should be able to look at this molecular formula of C8H10N4O2 and be able to answer the question, is this formula an empirical formula? And the answer to that is no, it is not an empirical formula because you can further divide or simplify those subscripts on those atoms by 2. So you should be able, at this point, be able to identify and define what structural formulas, what molecular formulas, and what empirical formulas are. So just a little review before we jump into the main meat of this little video, which is problems 1 through 4 with caffeine. First, formula weight in atomic mass units of caffeine. So to find the formula weight of a molecule, you'll need your handy dandy periodic table, and you'll sum up the masses of each of the atoms in your desired molecule. So for caffeine, we have 8 carbons, so we have to take the mass of carbon from your periodic table, 12.01, multiply it by 8. Do something similar with the hydrogens. There's 10 hydrogens, 4 nitrogens, and 2 oxygens. Doing that appropriate multiplication and addition, you get 194.22 atomic mass units. That is the mass of one molecule of caffeine in atomic mass units. What's more useful to chemists is the molar mass of a compound, because molar mass uses the units grams per mole. And grams is something that we can easily weigh out in the lab. What's nice about how the periodic table is set up is that to find the molar mass of a compound, you can find it exactly the same way as finding the formula weight. It's the same number, you just change the units. It's no longer AMUs, the units are now grams per mole or per 1 mole. So for every 1 mole of caffeine, I have 194.22 grams of caffeine. And this molar mass is going to be very useful to us for the rest of these problems, because we're going to use it to determine how many, at least in number 3, determine how many moles of caffeine we have. And we can do that because we now have a conversion factor through the molar mass to go from grams of caffeine to moles of caffeine. So we start this problem just like we would any other unit analysis or unit conversion problem. Write down the number and the unit that we're given. Give ourselves some space to work the problem. Write down the unit of what we're looking for. And then we see we have to go from grams of caffeine to moles of caffeine. The way we go from grams to moles of the same substance is through its molar mass. So I'm going to take that molar mass that we calculated in number 2, which was 194.22, and write that appropriately as a fraction, as a conversion unit. So my gram units cancel. I'm left with moles in the numerator because that's the unit I'm looking for. So doing that division, 0.050 divided by 194.22 should give you 2.6 times 10 to the negative 4 moles of caffeine. So that's how many moles of caffeine we have in this amount of grams. Now we want to know how many molecules of caffeine that is. And so anytime you see the word molecules, atoms, ions, things that we count in chemistry, start thinking about, oh, maybe I need to use Avogadro's number, or that special number 6.02 times 10 to the 23rd to convert. If you remember, 6.02 times 10 to the 23rd of whatever you're counting is equal to 1 mole of whatever you're counting. Well, I already know how many moles of caffeine I have in that particular amount of grams. So I can start my conversion problem with using moles of caffeine that I calculated in number 3, because that's how many moles are in 0.050 grams. Write down the unit I'm looking for, and then write down my conversion factor, which is Avogadro's number. Write it down appropriately so my units cancel. I'm left with molecules of caffeine in the numerator, which is what I'm looking for. And once you do that multiplication, you should get 1.6 times 10 to the 20 molecules of caffeine. So that's how you go about doing these first 4 problems. It's finding molar mass and using both definitions of a mole, specifically molar mass and Avogadro's number, in doing calculations. In the next video, we're going to talk about how to use the actual chemical formula itself to relate part of the molecule to the entire molecule.